All right, recording started. Now sharing the screen. All right, in the previous lecture, we mentioned about the electric strength of the cable. So we mentioned that the cable has two diameters. There is the inner diameter and the outer diameter. So DC is called the conductor diameter, and DI, which is basically the diameter for the whole cable. So there's the conductor diameter and the diameter of the whole cable, as we see here in the previous picture. So we can say again, from here to here is this, or I mean the DC, like the one in the red, which is the diameter. This is the diameter of the conductor, and the blue one, which is DI, the diameter of the cable. Then we mentioned about calculating the electric field. So here's like the capacitance, and we mentioned about the electric field. Then we realized that the electric field will be maximum at when 2V divided by DC ln DI by DC, and will be minimum at the outer. So will be maximum inside, when will be less outside of the cable, or inside the cable. Then we need to calculate the economical diameter of the conductor. So in order to calculate that, we need to identify the breakdown strength. So we need to make sure that the maximum stress is less than the breakdown strength, to be sure that we are on safe level or working safe. So the maximum stress less than the breakdown strength. That's our target. Therefore, we need to minimize the stress, which is the electric field. We need to minimize it. How can we minimize it? By applying the derivative and make the derivative equals to 0. So we can do the derivative here, d by dc, with respect to the conductor diameter maximum. This yields di divided by dc equals to E. As a result, we can say dc equals to di divided by E, or in other words, di divided by 2.718. Then this is the optimal ratio between di to dc to get the electric, to make sure we minimize the breakdown strength of the cable. That's our target. Then again, we have di by dc equals to E. Therefore, we need to calculate the maximum. Again, we know, as we know, E max equals to be 2V divided by, let me check it again, di ln of, let me check again, di by dc. Di. Let me check it again. Is it di? I believe it's the maximum at dc. Okay. This is the original maximum. But we need to make sure minimize the maximum to be as low as possible. So we call it Emax min. So Emax, which is the maximum electric field, and it's being minimized, so we don't want to reach the breakdown. That's what we mean by Emax min. Then the thing about it, we substitute the ratio di by dc, which is equal to E. This yields 2V divided by dc ln of E. And as we know, ln of E equals to 1. Therefore, it will be 2V divided by dc, and that's what we got here. So from this, we can calculate which is the maximum electric field when we minimize it to be, will not reach the breakdown at the optimal ratio between di by dc. So in high voltage cables, the value of the core diameter dc can be determined using the expression. So in general, the conductor cross-section is way much larger than the required from the consideration of the current carrying capacity. And the main reason is because we need to get this ratio. Now, stress distribution. So the overall, as we said, here the electric field will be maximum, then it will start be reducing here. Emax is being minimum. So since it's depending on the distance, so here when we have, for example, this is DC and this is DI, this one is DI. So we can say when we move away from the conductor, electric field is getting lower, which make it non-uniform. So the electric field is not uniform, is not equally distributed. So we realize that it will be in this relationship as we see in this red curve. That's something that we can see on the stress distribution. So then again, it has been distributed. It has been observed that the single core cable, the maximum at the conductor surface, and the decreases toward the metallic shields, as we said here, decrease when we move to the shield. In this cable, which has a homogeneous insulation, the thing about it, which is homogeneous, so the layer, all of them, the insulation material shares the same layer. Then we realize that the maximum voltage which can be safely applied by the cable is limited by the electrostatic stress at the conductor surface. So the thing about it, we need to worry about the worst case. So the maximum happening here, max happens here. Then we need to worry about studying this here at the surface. Again, which is make it non-uniformly distributed. So if the dielectric strength is high using the cable, then there is no dot. It is useful over the conductor where the stress is maximum. But as we go away from the conductor surface, the value of dielectric strength decreases. So the dielectric will be unnecessarily strong and expensive. So again, what we mean by this, when we do the cable, let me do it again here, the single core cable. Here is the core cable. Then we can say here is Emax. So we can put the material that can be here as very strong material. Then the other thing, here we need weaker material. So the thing about it, why do we need to make it homogeneous for the material? Why? I mean, if we make it like this way, all of them from the expensive material, this will be unnecessarily. Why? Because the electric field here is high, then we need to have a good material. But the electric field here is low, then there is no need to use expensive material. That's the thing. So if we keep it like this, then we must use expensive material because around this, around the conductor. But as we move away from the conductor, there is no need. So what we need to do, which is, can we make it as a layer? What do I mean by layer? Like the same thing as I did here, which is make the material close to the conductor, make it expensive, and make another layer material outer or away from the conductor to be cheaper with lower conductivity. And that's the idea. So I believe it's already been here. We will see the picture later. So the thing about it, so the stress can be distributed. So how about making the outer layer of the dielectric stress less than, while the insulation layer there will be expensive is inside and the less expensive is outside. Now let's talk about the grading of the cables. So the electric stress in the dielectric may be more equally distributed by one of the following methods. The first thing, which is called capacitance grading, and the other thing is called intersheath grading. So again, the overall idea, we will do something we call a grading, and that grading, basically, we will try to make the most expensive material close to the conductor, while away from the conductor, close to the metallic sheath, we will use a lower cost material. That's the thing. Now, there are two ways of doing this, the capacitance grading and intersheath grading. Let's talk about the capacitance grading first. So in this method, we will use different layers by different dielectric such that there will be epsilon r each layer, which is the same thing that, as I mentioned here, like there will be a layer and another layer, and we can make it multiple layer, not only two layers. We can make the red one layer, the red layer is, I mean, the most expensive. Then there's another cheaper layer in the blue. Then there is another the cheapest layer is in black. So as we move away, we will have multi-layers. This is called capacitance grading. Then each one has its own epsilon. We call it epsilon 1, epsilon 2, epsilon 3. Each one has its own radius. Then here's how it looks like. So here is epsilon 1, epsilon 2, epsilon 3, which is separating the dielectric materials. And that's what we have. That's what we already have in the cables. And so you can recall in the previous lecture when we mentioned about the high voltage cables, we mentioned that there is like about 12 layers in some of them. There is 9 layers in the other one and 8 layers in the medium voltage, 6 layers in the low voltage. So there was different type of layers. Therefore, what's the point? We need to make sure, since the electric field is, very large, close to the surface, we will make it here very expensive material. Then number 2, medium expensive. Then the cheapest one is number 3. Then when we look at it, we will see that the magnetic field is decreasing. Then once we reach the edge of the first layer to the second, the edge of the second layer, then the magnetic field is increasing. Why it's increasing? Because different epsilon, then keep decreasing, then increasing, keep decreasing. Our target, we want to make sure these peaks will not exceed the maximum allowable. Maximum allowable. That's the thing. Now let's go back here to see how can we do that. Again, we consider this as epsilon 1, epsilon 2, epsilon 3. Then there are different radius. The first layer R1 lowercase, R2 lowercase, and R3, which is the same as the cable radius, which is we call it R capital or R uppercase, such that we can say R, the same thing that we call it R conductor, or in other words, the diameter of the conductor divided by 2, then R alone, which is, we call it the resistance of the cable, or in other words, which is DI divided by 2. Then we have 2 additional more, which are those R1 and R2. So R1 here, we assume there are 3 layers. Then in the 3 layers, we assume the third layer ends at the cable diameter. So that's how we can do it. Then, therefore, when we look at this one, we will say that this is from here to here. From here to here, this is our conductor. Then from here to here, this is called R1. Here to here, this is called R2. Here to here, this is called R3, or in other words, we call it R, which is the R of the cable, or RI, or whatever you want to call it, R or RI, both of them. It's fine. So when we look at it, in order to calculate the capacitance for each part, keep in mind for area 1, area 2, area 3, when we calculate for area 1, keep in mind it is bounded between RC and R1. Area 2, it is bounded between R1 and R2. And area 3, bounded between R2 to R, which is the radius of the whole cable. That's the thing that you need to keep in mind. Then our target is to make all of them sharing the same max here and here and here at the entrance of each layer, all of them. This will be the max, Emax 3, Emax 2, Emax 1. We need in our design to make them, or we want to make them, all of them, they are sharing the same maximum value. So that's the optimal thing. We don't want to make it too much high. If it's too much high, it will exceed the maximum allowable. Or if it's too much low, you are spending money for unnecessary thing. That's why the optimal situation is to get the maximum here equals the maximum here equals the maximum here. To calculate the maximum at the first one, when r, or when the radius equals to r. This is the first max, happens at here. The second max, max 2, happening when the radius equals to r1. The third max happening when the radius equals to r2. That's, I mean, how we calculate the max. So when r, which is our conductor, rc, the second one when r1, the third one when r equal to r2. Once you understand it, it will be easy to follow. Then we just keep in mind they are all equal to each other. E max 1 equal 2 equal 3. Then according to Coulomb's law, so we can say the E equal to Q divided by 2 pi epsilon naught epsilon R1 times R1. Then we can say this is the same for E epsilon electric magnetic field 2, electric magnetic field 3. And Q is actually Q enclosed because, again, even though we have 3 layers, here's the conductor, even though we have 3 layers, but once we do the integral here, or do the integral here, or do the integral here, Q remains the same, Q enclosed. Because as we know, the dielectric times ds here is, according to the formula to find the Q enclosed, equals the integral of d, the dielectric materials ds. Then we can say the Q enclosed, we can say it's Q equals to the dielectric material, which is epsilon times E, then times the surface area, 2 pi times R. Then as a result, E equals to be Q divided by 2 pi R times epsilon, or we can say epsilon, which is actually the same as epsilon naught epsilon R. And that's how we observe this from, I believe, from electromagnetic, it used to be called Gauss law. I'm not sure, I think it's Gauss law for electric field. So maybe, I'm not sure if you remember this formula, but that's how we find this. So then when we do the substitution, all of them, they are sharing the same Q. We can say Q, Q, Q cancel each other. 2 pi, 2 pi, 2 pi cancel each other. Epsilon naught, and epsilon naught equal to each, cancel each other. Then what remains? Epsilon r times r. Then that's epsilon r times r. Here in terms of radius. Now, in terms of diameter, as we know, the diameter of the conductor equals 2 times the radius. Then the diameter number 1 equals 2 times R1. Diameter number 2 equals 2 times R2. Then this yields to this formula. This is a very important formula using 3 layers. And that's what we are using nowadays, especially in high voltage cables. Then we see epsilon r related to material number 1, epsilon r2, again, material number 2, epsilon r3, material number 3. dc is the diameter of the conductor, d1, the diameter of the first layer, and d2, the second layer. Again, this is the capacitance grading. This is how it looks like. Then, in order to calculate the total peak voltage across the dielectric, because again, here is the dielectric, and then we need to calculate the voltage. So the voltage will be the voltage of area number 1 plus 2 plus 3. And that's what we will do. So which is the voltage of number 1 plus 2 plus 3. Then V alone equals to E times R ln of, I would say, D or R divided by D by R capital or whatever. I think it's the opposite. That's what's supposed to be. Ln R divided by R. But here, if it is single core or single layer. But here we have 3 layers. Since we have 3 layers, it will be looks like this. Then this one is, you can compare it with the single layer formula. This is, a single layer, and this is the multi-layer. So the single layer should be lower, or the overall should be lower than the multi-layer things. Then when we do this, the analysis, we can make it in terms of the diameter. Once we make it in terms of the diameter, we'll just divide it by 2. The difference between number 1 and number 2, which is basically number 2 using diameters. And why we are using diameters? Most likely in cables, in high voltage, low voltage, and medium voltage, the way that we are taking it into consideration when our protocol is to use the diameter more than the radius. Now let's look at this example. A 33 kilovolts single core cable employing 3 layers. Oh, 3 layers, so we can apply the previous formula with the insulation constants epsilon r equals to 5 epsilon r2, 4 epsilon r3 equals to 3. Then the conductor radius d of the the conductor radius, so d of the conductor will be 2 times the radius, which is 2 centimeters, 2 times 10 power negative 2. Assuming that all 3 insulating materials are working at the same maximum stress, which means E1 equals to E2 equals to E3, this yields to be epsilon R1 times R1 equals times R times D conductor equals to epsilon R2 times D1 equals to epsilon R3 times D3. Then we need to determine the maximum operating voltage when we have the radius over the insulation 2.5 centimeters and the maximum 40 kilovolt per centimeters. Now, again, the information that we have, the radius over the insulation, the overall radius, the capital letter, 2.5 times 2, because it's, I'm sorry, it is, again, do it again. The radius is 2.5 centimeters times 10 power negative 2, while when we talk about the diameter itself, 2 times this, which is 5 times 10 power 2, power negative 2, or this is, or 5 centimeters. Then once we calculate the diameter of the conductor, the diameter of the insulation material, the relative permittivity, the Emax stress, we can apply this formula. dC equals epsilon R1 times D1 equals D1 times epsilon R2, etc. We can calculate the inner 2.5 D1, the other one 3.3. So as a result, we can say regarding to the radius, here is the conductor, here is the first layer, second layer, and third layer. So we can say the conductor radius is given as 1 centimeter. The second radius, here we calculated 2.1.25 because this is the diameter. Then the third one, or the second one, which is 3.33 divided by 2, which will be 1 point, 5. Let me just try to calculate it. 3.33 divided by 2, which will be 1.665. Then the last one is the outer. This will be, I believe, 5 centimeters. Again, the conductor radius 1 centimeter, the first layer radius 1.25 centimeter, the second one layer 1.665, and the last one 1.5 5 centimeter, 2.5, sorry, not 5, because we divide by 2, 2.5 centimeters. Now, to calculate the voltage using this formula, just substitute the values, then we realize the voltage is 50.36 kilovolt, but keep in mind, this is the peak value, not the RMS. We used to do the RMS value, that's our target every time. we used to say these voltages are the RMS. Therefore, we need to divide it by square root of 3 because as we know, the RMS equals the peak divided by root of 2. Then it will be 35.6 kilovolts. So as a result, this cable is supposed to be in 33 kilovolt single core. Then because of the capacitance impact of that cable, where is it? It will be 35.6 kilovolts. So the capacitance add something to the voltage. And that's what we mentioned earlier. The capacitance can impact the voltage as well. Now, if we solve the example with no grading, what do I mean by no grading? Which is only single layer. Only single layer. So when we do it, we can say V equal E max divided by 2, DC lane DI by DC. Then we calculated it 36.65 kilovolts. Then when we calculated the RMS, the voltage will be 25.9 kilovolts. So we realize that the voltage is lower than 33 kilovolts, while the previous one was higher than 33 kilovolts. So obviously, the cable insulation will fail if there is no non-graded cable, or if it is in single layer. Non-grading again means single layer. So in order to meet the criteria of 33 kilovolts cable, we need to make sure we have multiple layers. So difficulty with this method, we cannot obtain a wide range of permittivity in practice. So I mean, in practice, we cannot make epsilon R to be 1 or epsilon R to be 3 and 5, the same thing that we get before, because the permittivity, sometimes can be changed with time. That's something that we are worrying about because of the aging, decaying with the aging. And the other thing, which is when we do it, it will be difficult in the manufacturing process to make different 3 layers and will cause a high cost. Therefore, we will see or talk about the bonding of underground cable systems. So power cables have a metallic shield. This is the second method, using the metallic shield, not the layers. So along with this, with the voltages induced as a function of the operating current, in order to handle this induced voltage in both cables ends, we have to be bonded sufficiently to the earthing system. The following table gives the overview of this. As we see here, there is the earthing method, and there's the typical application. Then here we can see the both end bonding. This is most likely used in substations, short connections, usually in medium voltage and low voltage. The second one, single end bonding, usually used for circuits very short, up to 1 kilometers, very short. Then the method that I prefer to use, which is the cross bonding. This is the one. The cross bonding using high voltage and long distance connection where joints are required. So that's the most commonly used, is the cross bonding. This is the most commonly used, while single end bonding is usually only for short circuits. Then the both end bonding will be only in medium and low voltage, or even like in short connection. So both ends of the cables are shielded, connected to the system earth. And with this method, there will be no voltage at the cable ends because the cable ends is connected to earth. So no voltage, which makes it more secure. So which is both end of the cable shield are connected to the ground. On the other hand, circulating currents may flow. That's a disadvantage on the shield, as the loop between the two earth points. We will see as this in the picture here. So there will be the electric field will be here. The shield, there will be the voltage will be 0, but the problem is the ground loops. So there will be some ground loops going on here, some ground loops going on here. Then the expected waveform will be at both ends 0, 0. Then between them there will be some electromagnetic field. This is called both end bonding. And again, both end bonding, as we say here, this is used in substation, short connection, and usually in medium and low voltage. Then the disadvantages again is the economic impacts and the other thing, which is the circulating currents from the ground. The single end bonding, which is when cable is connected to the one shield, one side connected to the earth while the other end is open. And this is very common in circuits where they are less than 1 kilometers in very short distance. As we can see here, this bonding is connected to the earth, while this one is keep floating, not connected. There is, open. Then we realize that to calculate the magnetic field here is zero, then increasing when we move away from that area. Then the other thing, cross bonding, this is the best, and is used for long distances and used for high voltage and used also when we have a lot of joints. So this earthing method will be applied for longer routes length, again, when joints are required, due to the limited cable delivery. Across bonding method consists of 3 equal sections with cyclic shield crossing after each section. So there will be different sections, and each section where it will be grounded, as we see here. You see, this side is grounded and the other part is grounded. Then we connect all of these three together. Connect all of these three together for the 3 phases. Then here, and when we do this bonding, we can guarantee that the waveform here will be reduced. Without them, the expected waveform to be like this. But once we do this, in the middle, we are reversing this because we are just, when we can do this thing, so it will be like this. Just reverse it. So in this cross bonding, the induced shielded voltage in the section of each phase are equal to the magnitude, equal in magnitude and 120 degrees phase shifts. That's why when we do the sum between them, this will be 0. Because assume there is a vector here, then there is with angle 0, angle 120 degrees, and angle negative 120 degrees. If all of them, they are sharing the same magnitude, this yields the net force to be 0. Now, there are many criteria should be taken into consideration when we design the underground cables. So here is like some things, which is the first thing, system type. We need to make sure that we know about the operating voltage. So this could be, we need to make sure it is AC or it can be DC. The first thing that we need to make sure, is it AC or DC? Because right now we have some DC cables in HVDC. And when we are dealing with DC, keep in mind there is no inductance, no capacitance, no phase displacement, no surge problem in DC transmission, which make it easy for us. But this is not the 100, I would say this is in DC. While in AC you can see these problems. And the other thing, there is no skin effect on the DC as well. So cross-section of the conductor is finally utilized. And the other thing, the charging current in DC, which contributes to continuous loss or even on no load, which will be eliminated in DC. Then the DC line has less corona losses and reduce interference with communication circuits. In underground cables, they can be used for DC because they are less electric field stress and negligible direct electric losses. For the same load and sending voltage regulation for the DC is better. Voltage regulation is better when we have a DC. There are no stabilizers because there is a DC in case of we need to use a DC. So the only difficulty of obtaining the necessarily high voltage required for the transmission line, as neither electric power can be generated at high voltage, because commuting difficulties, no voltage can be stepped up. That's the problem in high voltage. We cannot step up the DC. We cannot use transformer. Cannot. I will fix it. We cannot use the transformer in DC. It's only used in AC. I mean, step up, step up, and step down the voltage using transformer is only on AC. How about DC? It's very difficult to make step up or step down in DC. So what we need to do using power electronics. Step up or down DC voltage. You can use power electronics. And power electronics as an example from the power electronics using buck boost. I'm not sure if you're familiar with power electronics course, but there is a device called buck boost. This buck boost can be used to step up or step down the DC voltage. At the early invention of the electricity, buck boost was not exist, so it was very difficult to step up and step down the DC. So again, the main advantages we can, or one of the things that we can do it, which is making it in AC system, we can step up or step down the voltage using the GSU, generator step up transformer, and step down transformers. But again, this is not in the DC. That's the advantage of the AC over the DC. Therefore, while to solve this issue, we can use AC, or you can use DC using buck boost. In the case of overhead lines, spacing between the conductors is kept more in order to provide adequate insulation to avoid the coronal loss. So like here is like in the power lines, this phase A, phase B, phase C, there is enough distance. So they can be isolated. While in the cables, they will be very close to each other, which is something can impact. Therefore, we have more copper is required in the underground cable, so greater the length of the transmission line, the more capacitance of the transmission line. And that's what we said on overhead transmission line. When we increase the length, there will be more capacitance. This can cause sometimes under light load condition, can cause something we call a Ferranti effect. Ferranti effect, which is the receiving voltage higher than the sending voltage. Then the construction transmission lines for AC systems is not easy as far as in DC. So in AC is more complicated. We need to worry about the stability analysis. We need to worry about the synchronization, the phase order, etc. So the three-phase stuff. So the generators need to be synchronized before they are putting on parallel. So in AC systems, they are superior by DC as in AC system voltage control, which is easy by using the transformer. The transformer has a tap changer, then we can do this in AC. So transmission of the electric power by DC system can be possible because of the power electronics. Again, power electronics like buck boost converter, or there is something we call it chuck converter. But the challenge about it's very high costs. The buck boost or chuck. The transmission of the dielectric power by DC has now become possible because of the power electronics again, but it is very costly. So these decide the type of the cable used, depending on the size, depending on how much voltage you need, depending on the overall cost that you have, the budget, and the other thing depending on the mechanical or how much you want to have the mechanical to the cable handle the mechanical strength, and if you need to use it unarmored, which will be cheaper. So sometimes we can say, do we really need the armor or not? So the armor will protect in case of, as I've said before, cables or in case if there is a fault, that will let the path for the current to flow. because sometimes some rats can eat the cables or some construction areas can impact the cable the quality, then we are using them for extra kind of protection. The maximum continuous current, so the area of interest in the underground systems or the conductor area, the I would say the loading conditions plus the overloading conditions as well. We need to make sure they are can handle it. It can handle the any unnecessarily or any expectation or any problem. We need to make sure it can handle a little bit, can contribute on it. So we need to make sure to complete the load cycle, plot it, then identify the maximum currents calculated in there. Then we can apply the applicable cross-section area for the conductor. Then we can underground use it in underground or can add future expansion. So the thing, we just do a study for the load, make sure what's the suitable size or the suitable diameter for the cable. Once you do it, we need to make sure it can handle the maximum. Voltage drop. The percent voltage drop must be calculated when the conductor of the cable is carrying full load current capacity, and the percentage should not exceed 5%. That's our target. The voltage drop must not exceed 5%. If it's exceed, then there will be some penalties or something that's out of the something that undesired we don't want. Short circuit currents. And this condition, one of the most dangerous conditions for the designers that we need to pay attention of, which is basically sometimes even like sometimes it can be ignored, which is the short circuits. So by the power system can be damaged as well. Different parts can be damaged. Then we need to make sure the system should be protected properly. So the full symmetrical and unsymmetrical faults analysis must be conducted in underground systems to make sure it can have sufficient acceptable values or the fault current can handle the system without doing a bad impact or damaging equipment. That's our target. Underground cable selection, again, one of the other factors that we need to worry about, which is economics. The optimal size cable, as we mentioned before, the running cost of this size and other different sizes. Beside this, other factors such as standardization of the cable sizes, future expansion, and protection of the power system. All of this impact on the cable size selection. So sometimes like, do we need to make a future work of it? If not, how about the cost? How about the cable size? How about the standards? How about the protection of the system? That's all these factors must be taken into consideration. Let's look at this example. Choose the right size of a three-phase copper with 400 volts. Underground earth cable at the temperature 20 Celsius degrees to serve in the area of 100 kilowatts consumption at the power factor 0.8. The length of the underground cable is 250 meters. It's short. And the fault occurred expected for this area is 25 kiloampere. Oh, wow, it's too much. But the protection power system has a trip of 0.2 seconds and making sure that the percentage voltage drop should not exceed 5%. So the thing, we need to calculate the right size that can handle all of these conditions. So the first thing, we need to make sure that the temperature will not exceed the 20 Celsius degrees. Then the converging factors, the real power equals square root of 3 V load times I load times the power factor of cosine theta. Then we can calculate them because we already know the P which is given as 100 kilowatts, the voltage which is 400 volt, this is line to line. Then we need to convert this to line to neutral. That's why we divide by 3, root of 3. Then, or just like, if you want to keep it like to line, you can say times square root of 3. Then you can say cosine theta, which is the power factor. Then as a result, we can say I load equals to complex power divided by square root of 3 times V load cosine theta. That's the currents. That's how we can do it. Or if you need to substitute it as line to neutral, which will be S divided by 3 V line to neutral cosine theta. And the way that I did prefer this, I prefer the first one, which will be easy. Now, for future expansion, should it take into consideration there will be addition 10% to the value of the currents. Now let's calculate the new currents. It was 181, then times 10%, which will make it as 199. So we will need to select the cable size that can handle this area. Then from the cable, select the cable size as A equals 70 millimeters. Then that can carry 230 amps, which is sufficient for our current. This cable has a voltage drop of 0.57 and 57 ampere per meter. Then the total drop voltage will be VD times L times I nu, which is 199.1. That's what we calculate. Then the voltage drop will be V sending minus V receiving divided by V sending. Vs, again, it's called V sending. Then VR, which is the receiving voltage. All right, so we can do this ratio. It's very similar to voltage regulation ratio, but here just the thing, which is voltage drop percentage. Then once we calculate the ratio, we realize it's 7.1, and in this example, 7.1 exceeded the 5%. This is unacceptable value because it's exceeded. Therefore, in order to solve this issue, what we need to do, choose a larger cable size. So the cable size here, we assumed it as 70 millimeters square. So we realize that the 70 millimeters square will be insufficient to do here at 70 millimeters square. This will be insufficient here. Therefore, in order to overcome on this, let's increase thickness. So by selecting the cable size 95 millimeters square, then which has the voltage drop of 0.42 per ampere per meter, then we can calculate the voltage regulation, or the voltage drop will be VT times L times I nu, which will be 20.91. Then once we calculate the voltage drop, we can calculate the percentage, so which will be 400 minus 20.991 divided by 400, which will be 5.2. 5.2, it's still unacceptable. Then we need to improve it by adding, increasing the size. So how can we select the size? Now let's increase the size to be 120 millimeters square. When we increase it, we can calculate the voltage drop, which will be 17.42, and the percentage will be 4.3. This is less than 5, then yes, stop here. Therefore, we will say, let's use 120 millimeter square. This is the best. Now the percentage voltage drop is achieved. Now we need to consider the short circuit currents. All of them, what we did is the opposite, the voltage drop. Now how about the second thing, the short circuit? Here's the voltage drop, which is number A, second number B, which is the short circuit current. Then we said that for the selected will be 31.125 kiloampere. At that time, trip drop 0.2 seconds trip time, which can handle the higher than the expected, because the expected in this problem was 25 kiloampere. So we can say in our problem, the short circuit current, it can handle 31.125. That was for the previous example. Now, when we keep going, which will be lower than the necessary stuff, therefore we said that again, area. 120 millimeter square will be a great solution. All right. Now let's go to this example. Choose the right size of the three-phase copper voltage 400 volts underground earth cable at the temperature 35 Celsius degrees and the surface area 165 kilowatts. The consumption at the power factor of 0.85, then the length of the underground cables is 350 meters, that's what's given, and the fault expected current will be 20 kilo ampere with the protection power system has a third time 0.5 seconds and making sure that the percentage voltage drop should not exceed 5%. So well, that's what we need to worry about. The first thing, we will do the same analysis as what we did before, calculating the currents, then the Imax. After that, we can say that the current new will be 308. Then in order to calculate using the power will be 280. Then 280 with the 10% allowable, because the question says, or that's what we need to discuss about it. Then the next thing, we calculate the currents. So at the 120 millimeter square, it can carry the current about 315. Then we need to make sure, is this sufficient with the same temperature? So 315 times 0.84. So 0.84, which is basically related to the degradation of this. Let me see. Okay, then after that, we need to make sure Imax, when we calculated it, will be 265, which is below than 308. Then the other one maximum, if we increase the size to be 355 ampere at 20 Celsius degrees, then it will be around 298. And again, when you look at these values, they are unacceptable. We need to increase the larger area for the cable. I'm selecting 185 millimeter square that can carry around 400 at 20 Celsius degrees. Therefore, we can say that Imax equal 400 times 0.84, which will be 336, which is larger than 308. That's great. Then to calculate the voltage drop 0.28 times 350 times 308, then it will be 26.95. Then the voltage drop percentage can be calculated using the ratio, which will be 6.75. Then we realize this is not acceptable. How to fix it? Increase the size of the conductor. Because it's more than 5%. So again, this is unacceptable value. Therefore, we need to rank up or higher up the cable size, increase the cable size. So when we look at there is another one with the area 240 millimeter square. The voltage drop here is 0.21 per ampere per meter. Then the total voltage drop will be the voltage drop 0.21 times the length which is, where is it? 350 times 308 will be 22.64. Then the other one, the voltage drop can be 400 minus 22, 164 divided by 400. Then when we look at it, calculating the ratio, which is still unacceptable. We need to make sure it is below than 5%. So how about what we need to do is to increase the size of the cable by selecting the size of the cable 300 and so on. Once we get the problem, if it is below than 5%, we need to replace it with a bigger size and so on. Then to find this, the voltage drop and the percentage will be 4.85, which is less than the 5%, and this is acceptable. Here in this picture, there is a construction, and how they are doing the underground cables. You can see like here, they're digging the ground, then they put the conductor. We need to make sure the conductor does not, the conductor is not very tight, so we don't want to lose the power for the system, for the whole network. So the cable warning tab, there must be a warning tab above the cable. So there will be, once they put here the cable, then there must be a warning tab. So if there's some people, for example, need to make a construction area, once they start making the digging into the ground or digging into the area, they will see the tab. Then they will say, okay, there is an electrical thing, so we cannot touch it. So they don't want to touch the ground or touch the cables. In underground cables testing and fault location detection, as we said before, there's a device, it's called Megger, that can be used to identify the fault location. Now let's talk a little bit about some testing devices that are used nowadays to identify the fault location. Here's an example of the fault location. You see how it's like the insulation material is being melted, then the conductor is also, there was a short circuit, it's going on here, causes this damage. So the cable failure and the analysis. Let's talk about the cable failure. There is a mechanical failure. The mechanical failure, it can happen due to breaks, mechanical breaks, defects, or of sheath materials, mechanical punctures by the people when they are like digging into the ground, or machines by the compressor, or cracks due to sharp bedding or vibration. Whenever mechanical damage, this is called mechanical damage, occurs at the cable sheath, the entrance of the moisture to the cable will produce slow deterioration, which will cause the impact the lifetime of the, which is called the cable, that will do a bad impact on the insulation materials because of the moisture around it. So I would say that sometimes the mechanical failures can do some small cuts, but that small cuts will be very big, very severe, because it will allow the humidity to pass. If it's not being solved immediately, it will cause, eventually cause a failure of the cable, and it will impact the overall system. There's another one, chemical failures, like the corrosion of the outer jackets. It can happen due to the soil effects, galvanic action, acidity on the around it, chemical contaminations on the soil. Corrosions of the outer jacket will eventually allow moisture, to penetrate through the insulation system and cause failure. That's something that we don't want. The chemical and mechanical, it can cause a failure in the future. Sheath corrosion can be minimized by correcting the application of insulation, insulating painting, providing the drainage, and removing the source of the chemical contamination. The other thing, the moisture in insulation, again, the moisture in insulation can be very dangerous, and it can happen because of the mechanical damages, or the previous one, which is the the mechanical damages, or the chemical failures as well. Those can impact the overall, can be impacting on the moisture in the insulation. So the moisture will start deteriorated to the cable. Then we need a precaution that should be taken to prevent so we need to make sure the moisture will not impact the internal material inside it, or the insulation material in the cable. So we can use or I would say like there is a bad effect in the damage due to moisture. When there is, I mean, a moisture, it will can cause these damages like a bleached or soggy paper, stain in the inside surface or the outer jacket, visible water, and whitish powder, aluminum conductor, and the armor. Now, let's talk a little bit about some failures like electrical failures. So electrical failures can happen because of the overloading. In the situation if there is heat in the cable, it can increase, which lead the degradation of the insulation because overload means heat. And that heat can impact the insulation material. And once we rise the temperature in cables, it can be fine for a specific period of time. But once we increase it, if it is exceeding the certain temperature, it will impact the insulation cable insulation system. So once we reach this, it will do the burn it, or we need to replace the conductor due to that. So therefore, we need to make sure to maintain the lifetime by not exceeding the maximum value, or if it's exceeded for a very short period of time. Switched operation. In case of switching operation, there will be a sudden voltage rise because of the capacitance that can impact the insulation material because of there's over voltage, as well as the conductors on the sustained for a long time. Other factors impacting electrical, other factors should be considered. For instance, fire in the conductor or manholes can happen, or the barriers can be installed between large groups of the conductor to prevent fire damage. Lightning can also cause surge in the conductors to the cable. Therefore, lightning arresters should be installed to protect the cable where it is connected to the overhead transmission line. That's something that's very important. Then, therefore, lightning arresters should be installed to protect the cables where it is connected to overhead lines to minimize failure of the cable. Then other like we call it sabotage actions and car accidents can be added to the list. Cables distinct failure. There's first thing, cable testing, then there's a pre-location, identify where's the location, then cable tracing to just follow the cable to see where's the location, then pinpointing. They will say like there is a pin going on here, then do the cable identification and try to solve the problem. This is a Megger. The device is called Megger. Then how we can see if there is a fault, they will inject DC, let me fix it, injects DC voltage inside the cable and identify the fault location. This is called again Megger, and the DC source applied is based on DC. Here is an example. There was a fault, trip out, then they used the Megger to identify where's the fault location. Once they found it, using the device, they start digging, then they saw this problem here. So why we have this problem? This problem maybe because there was a joint was not being conducted very well, tied very well, or because if there was a rat or something that causes the short circuits, then causes a problem. Again, here's like the conduction. So there is, we connect we call it megometers, or we can do like the Meggers, like as we said, like we used to call it Meggers. Then there is like GL and E. Then there is the insulation. There is the material or all material. Then we have the ground. We put one side of the DC on the cable side and the other one on the ground. I would say like the opposites. L with the line and E with earth. Here connected to line. Here is connected to earth. Then we do the test. How about DC testing? Again, all of them are called DC testing. That was for single core. Now, how about if we need to do it 3-core? Then the thing, what we will do in it, we will do the same thing. This is live or the positive. This is neutral. This is or for the negative. This is the positive. This is the negative. Then we shorted all of the phases together, or we shorted 2 phases. This one and this one are shorted, connected to the ground, while this one is still being connected. So the overall idea, how can we do to identify the fault location by applying a DC? This is a DC source. Then we will do some things called Watson bridge. So in Watson bridge, we have a predefined resistor RB, another defined resistor RA. Then this is the good conductor. And this is the faulted conductor. The overall length of the conductor is L. The faulted conductor L minus X. And the X here will to identify the fault of the location. Then we can say this is RB and here is C. So no, we just adjust to make sure the galvanometer reading is 0. Once the galvanometer reading here is 0, we can reach that RA equals to RA times RC equals RB times, I would say, RX. Then we can calculate Rx, which will be Ra times Rc divided by Rb. And Rx, by the way, we can apply rho times L over A, or rho times X over A. So A, Ra, Rb, Rc are known. Rho is known. Cross-section area is known. The only unknown is X. Then we can find X. Once we identify X, then this is the fault location. Okay, any question? Now, I believe we are done with the cables. Next lecture, inshallah, we will go to another topic. Let me stop.